Hi and welcome to video 9, unit 4, topic 1 of the Math Methods curriculum. We're looking at the second derivative and specifically we're looking at optimization. Again with a measurement type question, but this time we're dealing with a three-dimensional problem and we're looking to maximize, notice I'm always looking for that word, maximize the volume of the cone. And here's the cone here. So I'm going to have to refer to my formula sheet first of all before I do too much work and try and determine, well, how would I find the volume of a cone? And the volume on the formula sheet is 1/3 pi r squared h. So what I need to do now is go to my diagram and indicate where my r and my h are. So there's r and there's h. And that's for this particular cone. Now this particular cone has a diameter of 12, which means that this length here, which is the radius, is 6. That still doesn't give us a very good connection. Because the problem we've got at the moment is that while I haven't really fully defined all my variables, V equals the volume of the cone, and we're dealing with centimeters here, that's not how you spell cone, so centimeters cubed. R is equal to the radius of the cone, and it is a variable, unlike the radius of the sphere that is inside, or the hemisphere, which is set. So that's centimeters, and h is equal to the height, which is also in centimeters. So it's good to define our variables. Now we've defined them, we've got a volume formula, but we've got r and h connected in that formula. I need to eliminate one of them in order to move forward. So how do we do this? Let's have a closer look at this diagram. Now this is a really common type of question. In three-dimensional cases involving cones, this is almost always the way that we get through the question and how we usually relate height and radius. It's going to be through some form of either trigonometry, if we're told something like what this angle is, or Pythagoras theorem, because in this case the radius of the sphere or the hemisphere is 6, and whilst that is one representation of the radius, here's another. Because remember, the radius just takes you from the center to the outside. So this is also 6. And now all of a sudden we've got this lovely, everybody's favorite triangle with a bit of Pythag in it. So this is 6, this is height, this is radius. Because it's a cone, we have a right angle there, and we get h squared plus r squared equals 6 squared. And we can now eliminate h or r. Now again, you've seen this before, but let me remind you. H looks like the obvious one to eliminate because it's by itself already. So I rearrange here and I get something like h is equal to 36 minus r squared square root. And then I need to derive a square root function, which is a little bit annoying. So if we make a clever choice in this case, we can actually see, I meant to delete that h, that r is a better choice. So when I did h, I got that. If I do r, I can get down to r squared is equal to 36 minus h squared, and I can just use that representation and just take r straight out. There's no square root because I'm substituting r squared out, not r. And so I get this, v is equal to 1/3 pi times r squared, which is 36 minus h squared, times h. And now I can simplify this. 1/3 pi times 36 is 12 pi minus, oh, then there's an h on the end, 12 pi h minus 1/3 pi h cubed. And then dv dh, I've used v dash and s dash before, but I kind of should use dv dh because I need to tell the marker that I'm using dv dh as opposed to dv dr, which is the other one we could be using in this question. So it's good to make that clear. So I get 12 pi, and then here the 3 comes down, I end up with pi h squared. Now I'm going to let dv dh equals 0. I want the gradient to be 0 to get a minimum or maximum, and then therefore 12 pi minus pi h squared equals 0. Pi h squared equals 12 pi. H squared equals 12, and h is equal to 2√3. So I've got a value for h now. And now I can use that value to determine a value for r. Therefore r is equal to the square root of 36 minus h squared. Square root of 36 minus h squared is 12, remember? That's equal to the square root of 24, which is equal to 2 root 6. If I need it, but the question is actually asking, find the maximum volume. So I can go back to my volume in terms of h, which is this one here. And so therefore, volume is equal to 12 pi times 2 root 3 minus a third pi times 2 root 3 cubed, and this will simplify nicely. 24 pi root 3 minus, and this will be pi on 3, or third pi, times 2 cubed is 8, root 3 cubed is 3 root 3, so it's 24 root 3. And so I end up with 24 root 3 pi minus 24 root 3 pi on 3, which leaves me with 48, and you can do this in your calculator or do the calculation. Pi root 3 over 3 is my volume in centimeters cubed. And 48 divides by 3, which is nice, so 16 pi root 3, or approximately 87.06 centimeters cubed. So there's my volume. Now just going back through, as we will, tradition says, we've got interpretation here and a little bit there. Remember, I did that early. We've got defining variables and relationships here and here. Then we've got using relationships to get volume by itself in terms of one other thing there. And then we've got step 4 here and here. And then we've got, we didn't actually do step 5, so be very careful. Step 5 would be d squared v dh squared, which is equal to, in this case, negative 2 pi h. And then at h equals 2 root 3, d squared v dh squared is equal to negative 2 pi times 2 root 3, which is negative 4 pi root 3. We don't care what the value is, we just know it's negative, and therefore we're dealing with a maximum, which is good because we want it to maximize. This will always fit what you're expecting. And so that was step 5, and then this is step 6 to finish the question off. So there we have a completed solution for question 6, or example 9, which I've stolen from somewhere, and it was called question 6 where I've stolen it from. All the best.